All right, hope everybody had a good weekend. Back to another Monday here. Hope everybody enjoyed your M&Ms on Friday. There was sharing there also, you could have done too. Any questions you have on the M&M lab? Anything that we went through that I tried to explain as much as possible on Friday what we had to do with that. Is there any questions that you have? We turn it into that. You'll be able to, you can turn it in at the end of the period, that is fine. Okay, I'll collect them at the end of the period. Any questions that you have? Once again, the front page, use your empirical data from the table there and do your calculations like we did normal probability calculations. The second probability on the very backhand side, that's your data that you have in regards to the experiment. Okay, the experiment that you had, how many out of 60 met those conditions? Okay, so you're not multiplying any probabilities together on the back side. You're just looking at the data from the experiment and looking at how many out of 60 were those conditions, were both red. There was no reds in there. So you're looking at the data from the experiment. Also, you should have a little paragraph at the bottom of the back page as for a summation of your data, compare the data, see what happens with respect to the data from the front page to the back page. And they also ask for a reason why, and I'll get you. Okay, once again, you can hand that in at the end of the period here if you're done. If you do not have it done today, please have it done and completed for tomorrow. Okay, so you have a little reprieve there. Okay, another thing we talked about on Thursday was a binomial distribution, probability, probability distribution. Today we'll talk about binomial probability distributions. But when you talk about probability distributions, once again, we start combining the ideas of what we talked about with respect to probability, but also statistics. Okay, so you could do the histogram that we did with statistics. We gathered data and we did histograms and did frequency diagrams with respect to statistics, just numerical values. When we deal with probability distribution, we now start combining the idea of looking at probability and doing a probability graph, okay, a frequency probability graph, okay. So we start looking at the mean and the standard deviation with respect to probabilities, okay. So you have ways and means of being able to calculate those values. Okay, had a worksheet we handed out on Thursday. Any questions that you have? And once again, you're doing a probability distribution graph, which is like a histogram, but now you're just dealing with probabilities. You need to make sure, for example, in number 7 on the back-hand side, okay, I give you the number of overtime hours, I give you the number of employees, but I do not give you a probability. What you have to calculate is you have to calculate a probability of each one of those existing. So you have the probability of 0 hours is 6 over the 192. The probability of 1 hour is 12 over the 192, and so on. So you have to calculate the probabilities on the back-hand side. Okay, if you would just do a frequency diagram in regards to, or a histogram with respect to the number of employees, that would just be a histogram. That deals with statistics. What's being asked of you there is a probability distribution graph. I'm asking for probabilities. So we are dealing with probabilities on our graph on the vertical axis there. Questions on anything? Okay, know the difference between a histogram, which is just your data values, and a probability distribution, which is you may have to calculate your probabilities and then draw your data or your graph down there. All right, today we're going to talk about probability, binomial probabilities, which is sort of like a subset of a probability distribution. Once again, we're going to be dealing with a binomial experiment. It's going to be a probability experiment, okay? But when we're dealing with a binomial distribution, a binomial experiment, 4 conditions must be met. The first one, there must be an exact or a fixed number of trials. You have a fixed number of trials. Each trial must have exactly 2 outcomes or could be reduced to 2 outcomes. So you must have a fixed number of trials to begin with. Each trial has 2 outcomes or can be reduced to 2 outcomes. So there must be a fixed number of trials, and each trial must have exactly 2 outcomes or can be reduced to 2 outcomes. A true and false test. The answers to true and false tests are either true or false. You don't have a maybe there as an option. It's either a true or a false answer. Shooting a free throw. You either make it or you miss it. You don't get a half a point because you drew some iron up there. Okay? You either make or miss. Okay, those are easy ones to see. Because those are either make or miss. A multiple choice test with 4 options can be reduced to correct or incorrect. Even though you have 4 options there, you have 4 options. You're either going to have a correct answer or an incorrect answer. ACT. How many options do you have with ACT? Is that 5, 4 or 5? Is it 5 options? Yeah, 5 options there. So in the ACT test, You have 5 options. You have 1 correct. You have 4 incorrect. If you were guessing on an ACT test, what percent chance would you have of guessing something, the question correct? 20% chance. You have a 1 out of 5 chance, which means we have a 4 out of 5 chance or an 80% chance of guessing incorrect. Okay? Most of us, if not all of us, have taken the ACT test already. Okay, the proctor of the ACT test, you'll be sitting there, you have 60 minutes to be able to complete something or a section of the ACT test. Okay? 60 questions. You have 50 questions, 60 questions. Okay, last 2 minutes or last minute, they're going to say, all right, you have 2 minutes left. You're sitting there, you have 10 answers left to do. 10 answers left to do. They go down to a minute, you're now down to 8 answers left to do. You don't have enough time to read through all the questions. So we guess on the last part because you don't get any penalty for guessing. Okay, there's no penalty there if you get it wrong. So you guess on the last 8, 9 questions. How do you guess? Do we zigzag to make a pretty little design there? How do we guess? Well, there's a 20% chance of getting it correct, 80% chance of getting it incorrect. How should you guess if you have to guess on the last 8, 9, 10 questions? How should you guess? Yeah, straight down the line. Don't make a zigzag there. Go straight down the line. You're hoping that you get 2 or 3 of those correct. There's a 20% chance of guessing there. If you zigzag, you may miss them all. You may miss them all. If you go down the ladder, there's a chance you'll get 2 or 3 of them correct. We'll come back to ACT here. Third condition. Third condition. The outcome of the first trial, or outcome of each trial is independent. The first question being false has no bearing on the answer of the second one being true or false. Each of the questions are independent. The bearing of one does not have an effective bearing on the other. You have that wackadoodle teacher. Gives you 10 true and false questions. 10 of them. He makes every one of them. You do the first one. First one comes up false. Do the second one. Second one, you're ready to go. Oh, I know that one's false. You got false there. So you start thinking, okay, true is due, true is due. Third one goes in there. Read it. I know that one's false. So the third one's false. You got 4, 5, 6, 7, 8. They're all falses. You go to 9, you're saying true is due. It comes up false. You do number 10, that's also false. Okay? That wackadoodle teacher made every one of the true and false questions false to play psycho games in your brain. So what do? You go back over every question again. One of these has to be true, because no teacher would do that. No teacher would give you 10 true and false questions and make every one of them false. That's psychological games that they're playing on you. The warfare. But they're all independent. You can flip a coin 10 times. It comes up heads every time. It could happen. Probability of each trial remains the same. Probability of each trial remains the same. These four conditions must be met to be a binomial experiment or binomial situation. The outcomes of binomial experiment and corresponding probabilities of these outcomes. Okay, when you're talking about a binomial distribution, it's the outcomes of a binomial experiment and the corresponding probabilities of these. Is what we talked about last Thursday. When you had just a probability distribution. When you have probability distribution was you had your sample space along the bottom edge. You had your sample space. We had our sample space and we have our probability here. That's what we did last Thursday. It's the exact same thing here, but now there's just two outcomes. You just have two outcomes. Is that a symbol for probability for success? The symbol for probability for some success. And P, little p, is the numerical value for that. What is your probability for success? Guessing on the ACT test, probability for success. Okay, that's 20% chance. Then we have probability for failure. And Q is the numerical probability for failure. What you must determine in each one of these problems, or as you go through these, what is your success and what is your failure? Okay, and when you're talking about what is your success, you're looking at basically what is the question asking you for there. And we'll go through a problem where, even though we're talking about probability of success, it's not something that's a positive thing. N is your number of trials, and X is your number of successes in N number of trials. So you have N number of trials, and you have X number of successes in those trials. And this value of X will be somewhere between the N number of trials and 0. And once again, we go, your number of successes could go up to your number of trials.
I apologize, we got a little late start this morning. We will be having retake pictures this morning. We're going to start with the freshmen. Any freshman, A through, with a last name beginning with A through M. Please report to the auxiliary gym at this time if you plan on having your retake pictures taken. Thank you.
How we calculate a probability for X number of successes. In a binomial experiment, probability for X number of successes, P of X, and N number of trials. How we calculate our probability for success. Well, we go into our factorials again. We have N divided by MSN times X. It's Monday morning, we need to wake up. We have P, which is your probability of success, so the number of successes as an exponent. We have Q as your number of failures to the N minus X power. Get that down here and we'll talk about this in a second. How we can sort of simplify it in our brain, basically. We can always go back to equations and looking at and applying equations, but we can also simplify things in our brain. That's my job, is to help you do that. We've seen this before, and where we've seen this before, this is just NCX. Remember when we're talking about combinations, order is not important. Order is not important. So we have NCX, P to the X, Q to the N minus X. All right, to simplify this a little bit. NCX, we have number of trials, X is your number of successes. P is the probability of success, X is the number of successes. So we have number of trials, C, number of successes. Times your probability for success, to the exponent number of successes. So we have probability of success to the number of successes times the probability of failure to the number of failures. So you have probability of success to the number of successes times the probability of failure to the number of failures. I'm going to change this question here, and let's take a look at the ACT. ACT. We're going to guess on the last 10 questions. We're going to guess on the last 10 questions, and we're going to determine what's the probability of getting, let's say, guessing 3 of them correct. Probability of guessing 3 correct. Okay, we're going to guess. Last 10 questions, we want to know what is the probability of guessing 3 of them correct. Well, if we took a look at blanks, we've already established there's 5 options here. Okay, so if we take a look here, what we're doing down at the bottom, we have N is 10, we have 10 questions. we want to guess 3 correct. So the number of successes that we want is we want 3 of them. The probability for success we established up above. We have a 1 out of 5 chance. Or a 20% chance. Probability for failure we established is 4 out of 5, which is 0.80 or 0.8. We have 10 of them, we want to guess 3 correct. So if we take a look at these blanks, we want 3 of them correct, that means 7 are incorrect. Now, it does not matter which ones are correct or incorrect. We can have 0.2, 0.2, and 0.2. Those 3 we guessed correct. The last 7 we guessed incorrectly. Which is 0.8 for all of them. So the first one is correct, and the second one is correct, and the third one is correct, and the fourth one is incorrect, and the fifth one is incorrect, and the sixth one's incorrect. Well, I'm throwing the word "and" in there. What operation do we use when we use probability in the word "and"? Multiply. So all these get multiplied together. But let's take a look at this. What if I went correct, correct, incorrect, correct? Or correct, incorrect, incorrect, correct, incorrect, incorrect, correct? There's many different options there. Does it matter what order we're in here? No, just so that we guess 3 of them correct. Well, when we talk about the idea of combinations, order is not important. So we have 10 options there, or 10 questions, and we're choosing 3 of them and putting them in different order. So once again, when we're talking about the idea of combinations, it doesn't matter what the order is. Now, if we take a look, we have 0.2 times 0.2 times 0.2, or this is 0.2. How can we write that mathematically? If I'm multiplying 0.2 to itself 3 times, I can write that as how? 0.2 to the 3rd power. We can cube that. Times. Then we have 0.8 there. We multiply that 7 times. So we have 0.8 to the 7th power. Here's our combination, 10C3. Our probability for success to the number of successes times the probability of failure to the number of failures. So this is what I can clickety-clack through my calculator. So I have 10C3 times 0.2 to the 3rd times 0.8 to the 7th. What did we come up with? .201, .201, which is a 20.1% chance that you will guess 3 of them correct. So you have a 20% chance of guessing 3 of them correct. So if I nomenclature this, the probability of 3 successes This would be, the 7 would be the 10 minus 3, which is the n minus x. If you want to put it into this term right here. But once again, I think it's easier not to get stuck on the idea I have to use a formula, where I have number of trials, number of successes, probability for success, the number of successes, times the probability of failure to the number of failures. I can do my calculations at that point. Those that have your stat book, grab your stat book. If you don't, you need to share with somebody. You might want to bring it for the rest of this, to the rest of this chapter. If you go to the back of the book, on page, you have Appendix B, and you flip the page to page A8 and A9 and A10. What you have there is what is called a binomial distribution table. That calculates a lot of probabilities for you. If you look at the top of page A9, you have the left-hand side, you have an N at the top of this table, then you have an X. N is the number of trials. X is your number of successes. Then along the top side of the table, you have all these p-values. That's your probability for success. Well, in this case here, our p-value was 0.2. So if you go over to 0.2 along the table there, we want 3 successes. So you want to drop the 0.2 down to the 3. And the value that you got there is 0.201. Okay, so this probability table will give you your probabilities. Now, this only works if your probabilities are multiples of 5. Your p-values are multiples of 5. If your p-value is not a multiple of 5, you have to go to this equation right here. Now, when you want to use this table is when you have multiple values that you have to calculate. I will set up the problem. If you have to calculate multiple values, you can pull these values from the table. If you have to calculate one single value, I will give you probabilities that aren't multiples of 5. But if you have to do multiple values, I will give you probabilities that are multiples of 5. So you can pull these values from the table. There is a method to my madness. So if we take a look, we found that 60% of American victims of healthcare fraud are senior citizens. 10 victims are chosen at random. Find a probability exactly 3. Well, that's what we just dealt with here. We can calculate that. Find a probability at most 2 victims are senior citizens. At most. Well, when we're talking about at most, that means That could be probability of 0, 1, or 2. So what we have is we have 3 values then that we can calculate. We have to calculate. This is when you can add up or go to the table to find values from the table. Solutions are posted to you for you. Adios. Have a good day.